given the classical statements for second law of thermodynamics, and from those statements we have seen that it is impossible to construct a heat engine which will have cent% efficiency, or it is impossible to construct a refrigeration cycle which will have infinite COP or coefficient of performance. Then it becomes the logical question that what could be the maximum possible efficiency of a heat engine, or how we can construct a heat engine which will have maximum possible efficiency. So, in that regard I told that if the heat engine cycle is a reversible cycle, then we will have highest efficiency possible for a heat engine. And for a reversible cycle, we need all the processes of the cycle to be reversible. Then we started identifying what are reversible process and irreversible processes, and in that regard I told that if there is a change of state by a particular process, and if we can reverse the process in such a manner so that both the system and surrounding can be brought to the initial state without leaving any change either in the system or in the surrounding, then the process can be called a reversible process. All the natural processes are irreversible processes, but with all the processes different degrees of irreversibilities are associated, and there are some reasons which increases the irreversibility of the processes, and we started identifying different reasons for irreversibility. Now, we were making a listing like this: causes of irreversibility. There I have told that heat transfer across a finite temperature difference, that causes irreversibility. Mixing of two material, that causes irreversibility. Third, we can name that unconstrained expansion so this also causes irreversibility. Let me explain the last item. Let us say we have got a compartment like this, and in this compartment there is a partition. So, basically in this compartment we are having two chambers. In the first chamber we are having a gas with certain pressure, let us say the pressure is P, and in the second chamber it is a vacuum. Now, if somehow this partition is removed, then what we will find that the gas of the first compartment, it will occupy the entire space and it will have a different temperature, let us say P1. This process is a highly irreversible process, because if we want to come back to the initial condition, what we have to do? We have to put, let us say, some partition here, and then we should have some sort of a pumping device which will pump back all the gases from this chamber to the other chamber till the pressure in this chamber becomes P. So, we have to do certain amount of additional work. Not only that, while we are compressing the gas in this chamber, the gas temperature will rise and probably we have to cool the gas. So, we can see that from the surrounding we have to put some more effort, or there will be certain changes in the surrounding. So, though by some effort we can bring the system to its original condition to state 1, but there will be certain changes left in the surrounding. In other words, what we can see that the pressurized gas that is having certain potential for doing work, if we allow it to expand freely, this the unconstrained expansion is also termed as free expansion. So, if we allow the gas to expand freely, it is losing its potential of work because it is going through an irreversible process. Then we can have different dissipative processes. What are the dissipative processes? There are different processes which are known as dissipative processes. Some of the examples are like this, that there is friction. In ideal case, we do not consider friction, but in actual case we know that there is certain amount of friction associated between two solid surfaces. When we like to have a relative motion between the solid surfaces, so there will be friction and due to that friction some amount of energy will be dissipated, some amount of energy will be converted in some form which cannot be recovered easily or which cannot be recovered at all. So, this is a highly irreversible process. One can take different example where friction or dissipation due to friction is there. Similar phenomenon one can find in fluid flow. In fluid flow, we know viscosity that puts some resistance to the fluid motion, and obviously there will be some amount of dissipation of energy in the fluid due to the presence of viscosity. One can take the example of flow of current through some resistor. So, as the current is flowing through the resistor, there will be ohmic heating, and this is also a dissipative process. Some amount of energy will be lost due to this dissipation. These are all examples of irreversible processes. There could be some other, there are some other irreversible processes. In fact, there are a number of other irreversible processes. We are not going to list them one by one, but now we have some idea regarding what are irreversible processes. And while designing a heat engine for its maximum performance, one should try to avoid these irreversible processes, or one should select the processes where the irreversibility will be the minimum. Based on this logic, Sadi Carnot, he has postulated one cycle, heat engine cycle, which is a reversible cycle made up of reversible processes and which can perform at its maximum limit. Let us see how the Carnot engine or Carnot cycle is constituted. So, basically one heat engine cycle, let me draw it schematically, as we know, will be like this. There is a high temperature source at T1, there is a low temperature sink at T2, where T1 is greater than T2. Heat flows from the high temperature source, let us say this is Q1, heat is rejected to the low temperature source, Q2 amount of heat is rejected, and W amount of work is done. And from first law we know Q1 minus Q2 is W. So, in our heat engine cycle there should be one heat source and one heat sink. Carnot cycle also there is one heat source and one heat sink. Let us say this is our heat source and this is the heat sink. Heat source will give, or energy will be supplied from the heat source to this engine or to the Carnot cycle. Now, we know heat transfer across a finite temperature difference, that is an irreversible process. So, if heat transfer is inevitable for a heat engine cycle or for one process of the heat engine, so we have to select a process where there is no temperature difference. So, there is no temperature difference, but flow of heat is there. One can select a process if there is a phase change process. Let us say the process of boiling. So, if the fluid is at its saturation temperature, it needs latent heat for the transformation of phase, but there is no change of temperature. So, one can ideally think of a process like this, by which there will be heat transfer from the heat source to the Carnot engine. So, that is what I have written here, and let us say it is a boiler. It is an ideal boiler where there is heat transfer from a high temperature source and fluid is at its saturation condition. So, it is only picking up the latent heat and transformation is taking place from the liquid phase to vapor phase. So, after that there is expansion of the fluid and it is doing certain amount of work. So, basically the next component which I am drawing, that represents a turbine. So, it is doing certain amount of work, and in this process the fluid temperature is also falling. So, as there is change in temperature in this process, there should not be any sort of heat transfer, because along with temperature change, if we have heat transfer, then the process will become an irreversible process. So, basically this is some adiabatic expansion of the fluid. In the next step, we will have another component where heat has to be rejected to the low temperature sink, and here also this heat rejection process should take place at constant temperature or isothermally, and this can be done through a condensation process. So, the next component we can denote as a condenser. So, here we are having a condenser. So, now what happened, after the boiler we had the vapor phase has expanded through the turbine adiabatically. Then after expansion, its pressure is low, but still it is in the vapor phase. Then it has condensed. So, it is in the liquid phase, but its pressure is low. So, now we need its pressure to be raised, so that it comes back to its initial condition. So, we need another component here where pressure rise will take place. So, this component could be equivalent to a pump or a compressor. So, let me put this to be P, and this arrow mark shows the direction of fluid movement. Here in the turbine, it produces some external work. Now, this work should be sufficient to run the pump also, and the extra amount of work that could be given to the surrounding. So, from the boiler Q1 amount of heat will come, and in the condenser Q2 amount of heat will be rejected. Well, again in the pump we will have adiabatic compression of the fluid. So, basically we can see that Carnot cycle, the way Carnot has postulated, it is made up of 4 different processes. We can write down like this. Processes in a Carnot cycle. One is isothermal heat addition, second one is adiabatic expansion, third one is isothermal heat rejection, and finally adiabatic compression. So, these are the 4 processes by which a Carnot cycle is constituted. Now, the example which I have selected here, or the block diagram which I have shown here, it shows a flow process, okay, and it has 4 components which which to some extent similar to our conventional steam power plant. We have got a component like boiler, we have got a turbine, a condenser, then a feed pump. It is interesting to note that as all the processes are reversible processes, so they can be reversed, and the direction of fluid flow, that also can be reversed theoretically, and we can get another cycle which will be either a refrigeration cycle or a heat pump cycle. So, we can have something like this. There could be net heat transfer from the outside, and we can have the direction of fluid flow reversed like this. So, we can write this arrow, it indicates forward Carnot cycle, or it is a heat engine cycle, and this arrow, it indicates reversed Carnot cycle, or refrigeration cycle. It should also be noted that this is not the only configuration of Carnot cycle. One can have a compressible fluid inside a piston cylinder arrangement and can have this Carnot cycle, where these 4 basic processes like isothermal heat addition, adiabatic expansion, isothermal heat rejection and adiabatic compression are present. That means, what I mean to say is like this. This is a piston cylinder arrangement. All right. And inside this piston cylinder arrangement, certain compressible fluid or gas is there. Now, one can think of an ideal cycle where you are having two reservoirs. One reservoir is at temperature T1, another reservoir is at temperature T2, and T1 is greater than T2. Then you have got, this is the cylinder, and you have got two cylinder heads. One head is perfect conductor of heat and another head is a perfect insulator of the heat. So, what you do to start the cycle, let us say isothermal heat addition is our first process of the cycle. So, in that case perfect conductor will be fitted to the cylinder as the cylinder head, and it will communicate with the temperature, with the thermal source at temperature T1. So, isothermal heat addition will take place. Then at next moment I will remove this perfect conductor and put this perfect insulator here. So, now as the gas will expand, it will expand adiabatically. Then again in the next moment I will remove the perfect insulator, put the perfect conductor as the cylinder head and make a communication with another thermal source at temperature T2. So, isothermal heat rejection will take place. Then finally, I will remove the conductor, put the insulator, so that there is adiabatic compression. So, for this piston cylinder arrangement, if I draw the PV diagram, pressure volume diagram, I will get something like this. Let us say this is 1, this is 2, this is 3, this is 4. So, 1 to 2 is the isothermal heat addition and 2 to 3 is the adiabatic expansion. 3 to 4 is isothermal heat rejection and 4 to 1 is adiabatic compression. So, what we can get here, this is Q1 heat addition, Q2 heat rejection, and in the PV diagram the area of this particular cycle becomes the work done during the cycle. So, this much amount of work will be done by the Carnot cycle. In this case also one can reverse the direction of heat addition and work transfer, and if we do this we will get a heat pump or a refrigeration cycle. the cycle with this green dot, that indicates a reverse Carnot cycle, which is not a heat engine cycle, but a heat pump or a refrigeration cycle. Obviously, the direction of heat flow, that will also be different or reversed. Now, I think this gives us a good idea about Carnot cycle. So, which Sadi Carnot has proposed as an ideal heat engine cycle. Now, along with this, along with the proposition of this cycle, he has also given a few attributes or a few characteristics, qualities of these cycles. Two of them are very important. First one, so these are known as postulations of Carnot. What are those? First one, it says that if two temperature limits or two thermal reservoirs are given, if T1, T2, these two are the temperatures of two thermal reservoirs, if these are given, then all the amongst all the engines working between them, a reversible engine will have the highest efficiency. Let us say we have got two thermal reservoirs. The thermal reservoir, which is a source, that is having a temperature T1, and the other thermal reservoir, which is acting as a sink, that is having a temperature T2, where T1 is greater than T2. Then we know that we can run a heat engine between these two thermal reservoirs, and we have a number of thermal reservoirs in between these two reservoirs. Sorry, we have a number of heat engines in between these two thermal reservoirs. Then a reversible heat engine will have the highest efficiency. Now, one can prove this, though I am not going to do it in this class, it is available in any thermodynamics book. If we assume that an irreversible engine is having higher efficiency compared to a reversible engine, we will see that it will amount to violation of second law. So, as second law is a fundamental law of nature, it cannot be, it is never violated. So, it is not possible for an irreversible engine to have higher efficiency compared to a reversible engine working between same temperature limit. That is very important. So, always one should go to, one should try to build engines or cycle which are closer to reversible cycles, reversible engines. The second point is also important. The second point, it says for given T1 and T2, all the reversible engines will have same efficiency. So, this is also very important that if T1 and T2 are given, if two thermal reservoirs are fixed, then number of reversible heat engines are working between them, all of them will have same efficiency. What does it mean? It means the efficiency of the heat engine does not depend, or efficiency of reversible heat engine does not depend on the working fluid, working medium which we have selected. It does not depend on the physical size of the cycle or engine which we have selected. It depends only on one parameter, that is the temperatures of the thermal reservoirs T1 and T2. So, if these two things are fixed, then its efficiency is also fixed. This is a very important observation which Carnot made. Let us start from this point, that efficiency of heat engines, efficiency of reversible heat engines, that depends only on the temperatures of the thermal reservoirs. So, efficiency of heat engine, that is W by Q1. All right. Side by side, let me draw our old figure. This is W, this is Q1, this is Q2, T1 and T2. These two are the temperatures. That means we can write Q1 minus Q2 by Q1, or we can write 1 minus Q2 by Q1. So, this is the efficiency of a heat engine, and then this expression is valid both for reversible and irreversible heat engine. For all heat engines, this particular expression is valid. Then Carnot postulated that for reversible heat engine, this efficiency depends only on temperatures of the two thermal reservoirs. So, basically what we can see, eta heat engine, that is a function of, let us say, Q2 by Q1. Again, from Carnot postulation, we can see that this is another function of T2, T1. Okay. Of course, some sort of logical reasoning can be given for selecting this type of functional relationship, but it can be shown that the heat engine efficiency, if it is depending on the temperatures T2 and T1, one can write like this. So, there is a direct relationship between Q2 by Q1 and T2 by T1 for reversible heat engine cycle, and with some amount of logical reasoning and with the selection of a proper temperature scale, one can show for reversible cycles Q2 by Q1 is equal to T2 by T1. This is for reversible cycles. This is a very important observation. Again, it is a very important observation Based on this, one can define a thermodynamic scale of temperature. We know all the scale of temperature which are made earlier, they are dependent on some material property. Let us say expansion of a liquid, that could be one property by which a by which a temperature scale can be generated. But here, without taking any material property, a scale of temperature has been developed based on thermodynamic logic only, that is known as thermodynamic scale of temperature. Sometimes this is called that absolute scale of temperature also, and this temperature is referred as absolute temperature. Already we are familiar with this absolute temperature from our from our physics, from the knowledge of our physics, and that is why I do not want to elaborate much regarding this absolute scale of temperature, but the relationship to which I will draw your attention, which is very important, is this: Q2 by Q1 is equal to T2 by T1 for reversible cycle. If we extend this further, then we get something like this. Q2 by Q1 is equal to T2 by T1, or Q1 by T1 minus Q2 by T2, that is equal to 0. All right. Or if we take again this example of Carnot cycle, where there is reversible heat transfer, reversible work transfer. So, this is Q1, this is Q2, this is T1, this is T2, and this is W. So, we can write cyclic integral of dq by T reversible, that is equal to 0. So, this Q1 by T1 minus Q2 by T2 is nothing but cyclic integral of dq by T. If we consider these two figures side by side, this figure and this expression side by side. So, if we take dq by T, so what it is becoming for a cycle? This is becoming Q1 by T1, because this is the heat addition, and then heat rejection is Q2, that is taking place at temperature T2. So, as it is heat rejection, a negative sign will come, okay, a minus sign will come, and it becomes Q2 by T2, and then if we put the entire thing, it is equal to 0, which amounts to cyclic integral of dq by T reversible, that is equal to 0. Now, from the temperature heat transfer relationship of reversible cycles, we get cyclic integral of dq by T is equal to 0. If cyclic integral of dq by T becomes 0, of course, it has to be qualified that it is for reversible process. Then what can we conclude from this? We have got similar situation earlier in our first law. So, what can we conclude from it? Let us say there is a cyclic process like this. So, we have taken two arbitrary processes, any two arbitrary processes, 1 to 2, this is one process, and then 2 to 1, that completes the cycle. So, if we have to take cyclic integral of dq by t, so what we have to do? We have to compute dq by t from 1 to 2, and then we have to compute dq by t from 2 to 1. We have to add this quantity and we have to add this quantity, and if we do the addition we get 0. What does it mean? It means that dq by t, whatever path we may take, it is not dependent on the path, it is dependent only on the end state, and it becomes a property of the system. It is not a path function, but it is the function of the state point, then it becomes a property of the system. It is very interesting to note that dq, heat, time and again I have told, and we know also that heat transfer, that is a path function. It depends on the type of process or type of path taken by the thermodynamic system. If we have, let us say, I show constant volume process, we will have some amount of heat transfer. If we have some constant pressure process, we will have some different amount of heat transfer. But dq by t, it becomes a property, it does not depend on the path. If the end states are fixed, then the change in dq by t, that is also fixed. So, we can write down now dq by t, of course, we have to put this, it is for reversible. This is a property of the system, and this new property is termed as entropy. So, we can write ds is equal to dq by 2, where S is entropy. So, we are getting a similar situation as we have seen in case of first law. So, from the first law, from the discussion of first law, we could identify a new property which is internal energy or stored energy. Here also we are identifying a new property which is entropy. Okay. In that case, two path functions were involved, dq and dw. Here only one path function is involved, that is dq. And of course, we should not forget to put reversible, because this dq by t for reversible process, that only gives the property entropy. So, as it is a function of state point, we can do the integration easily. ds, let us say 1 to 2, that is equal to dq by t 1 to 2, and we can write in the next step S2 minus S1 is equal to 1 to 2 dq by t reversible. Obviously, the integration on the right hand side can be done if the relationship between q and t are known. If this relationship is known, then we can do the integration. But this is how we can calculate the change in the property entropy. Again, this particular relationship is also expressed in a different way. The basic relationship is ds is equal to dq by t. So, one can again write for reversible process. So, dq is equal to tds, and again it is for reversible process. So, from here if we do the integration q1 to 2, that is 1 to 2 tds, if the relationship between T and S, entropy and temperature, are known, then one can have what is the heat transfer during this process. What is the reversible heat transfer during this process? This we have to keep in mind, that the reversible heat transfer, if the process is reversible, then obviously the heat transfer is also reversible, and one can get it by this particular expression. Now, you see that temperature, that is an intensive property of the system. Entropy is an extensive property of the system. Of course, one can define specific entropy, entropy per unit mass, then it becomes intensive property. It becomes some derived intensive property. But these two are independent properties, and they can be used as two ordinates of a thermodynamic plane, and we can represent thermodynamic processes on Ts plane. As we are familiar with thermodynamic plane, where P and V are used, either we can use volume or you can use specific volume as two ordinates of this particular plane, as the two axes of this particular plane. Similarly, one can have Ts diagram. So, where T either entropy or the specific entropy, that can be used as another ordinate. So, thermodynamic processes, one can represent it on PV plane, one can represent it in Ts plane also. Now, if we represent it in Ts plane, then let us say there is a process like this. The process is represented by the curve AB, 1, 2. The area under this curve becomes heat transfer during this process. So, this will be Q 1 to 2. So, we can see that once we have got the property entropy, with that we can have thermodynamic representation of the process, and area under the Ts curve, that becomes your heat transfer during a particular process. Then you see the Carnot cycle, which I have represented in PV diagram, it can be represented in Ts diagram also. So, we know that there are two isothermal processes, one at high temperature, let us say T1. So, 1, 2, then there is adiabatic process and reversible adiabatic process. So, reversible adiabatic process becomes an isentropic process. So, 3. Then there is one isothermal heat rejection process at temperature T2, and then there is one adiabatic compression process. So, this becomes the representation of Carnot cycle in T s plane. And very easily I can get the efficiency of the cycle from here. Let us say the cycle efficiency, we are trying to determine it from our classical expression of first law, that is 1 minus Q2 by Q1, that is your efficiency. So, what is Q2? Q2 is the heat rejected, and this will be, if we call this point 4, then Q2 is equal to area of this particular portion, and that will be given by S3 minus S4 multiplied by T2. Similarly, Q1 will be given by S3 minus S4 multiplied by T1. If I substitute these values, then efficiency will be 1 minus T2 by T1, which we have got from the postulation of Carnot. I think we will stop here today, and next day we will try to see some more implication or some more significance of entropy. Thank you.